Okay. Alright, so we're going to get started talking about functions of the peripheral circulatory system and how the heart does most of the work for the circulatory system. It does the pumping, and then the arteries and blood vessels provide the route as well as a place for exchange, especially those such as the capillaries, arterioles, and venules. Okay, the peripheral circulation, its role is to carry the blood, exchange nutrients, waste products, and gases with tissues. It's also going to help regulate the blood pressure and direct blood flow to those tissues. Arteries. Okay, one thing to get to know about the arteries is they don't always carry blood that has oxygen in it. There's an exception to that, and that's going to be your pulmonary artery. The blood that goes from the heart to the lungs does not contain a lot of oxygen. It goes to the lungs to get oxygenated. Okay, so the thing that you could say that's always true of arteries is that arteries are always going away from the heart, okay, toward the capillaries where exchange is going to happen. Okay, blood flows through the elastic arteries, muscular arteries, and arterioles, and then eventually reaches the capillaries. And the capillaries where gas exchange, waste exchange, all exchange will happen in the capillaries. Okay, veins. Veins are just going to carry the blood back to the heart. Okay, so it's the recycling system for the blood. Okay, veins go through the recycling veins, or the blood does, and goes back to the heart to get pumped to the body again. Okay, they carry the blood to the heart through venules, small veins, and large veins. Okay, so here we can look at different types of arteries here. We have elastic arteries up top, as well as the muscular arteries, medium and large veins. Okay, notice that we have quite a bit of difference. The elastic arteries have what that the others do not have. Okay, the tunica media. Okay, the tunica media, as you can see right here, the tunica media provides the ability for the arteries to expand because they are elastic. Okay, muscular arteries and elastic arteries both have your base membrane, your endothelium and basement membrane. Okay, they both have some connective tissue, but your muscular arteries are going to be coated with a layer of smooth muscle. Okay, which, remember, smooth muscle is always auto-regulated, so it does not need an impulse from you to tell it to work. It works on its own. Okay. Medium and large veins. Veins are not nearly as thick as arteries. Okay, they don't have to be. They don't carry as much pressure. Okay, the blood that goes through them has much less pressure than the arteries. Okay, blood vessels. Okay. Except for capillaries, they typically have these three layers. The inner layer is called the tunica intima. Okay, it has endothelium, a basement membrane, and an internal elastic lamina. Then you got the tunica media, or the middle part, which contains smooth muscle and elastic and collagen fibers. Okay, and then the outer part, or the tunica adventitia. Okay. It just contains connective tissue as well to help hold everything together. Okay, so here we can look at the slide and we can see the three layers here, the tunica intima towards the inside. See the large opening here where the blood would flow through, the tunica intima, tunica media, or the muscle area, and connective tissue here, and then the outer layer of connective tissue, the tunica adventitia. Okay, arteries. Three main types right here. Large elastic arteries. Where are the large elastic arteries found? Okay, we'll find that out really soon. Okay, these are thick-walled arteries, and they have extremely large diameter, like the aorta. Okay, the tunica media has elastic fibers and little smooth muscle because it doesn't have to push to pump it, because places like the aorta have a lot of pressure built up just from the pumping of the heart. They need to be able to expand to keep from exploding with so much pressure that's placed on it by the heart. Okay, and then you have the muscular or the distributing arteries. These are further away from the heart and are towards the extremities of the body. These are thick-walled with small diameter, so there's more muscle than there is actually an opening for the blood. And the tunica media has a lot of smooth muscle and some elastic fibers. And then you get down to the arterioles, where you're getting closer to the capillary beds. These are the smallest arteries, and the tunica media, or the middle of it, consists of 2 layers of smooth muscle cells and a few elastic fibers. So here we look at the arteries. Looking at it again, elastic arteries versus the muscular arteries. We've gone over the differences and similarities a little bit already. Okay, notice the tunica media. Okay, one of them contains a lot more smooth muscle, and you can see the different layers in the muscular arteries. See how small the diameter is in comparison from the muscular artery to the elastic artery. Elastic artery, remember, has a lot of pressure on it, so it has to be able to expand just like a tire. Okay, capillaries. Once you go through all the arteries and you get to the tissues, you're going to get to the capillaries, where all the exchange is actually going to happen. That's the capillaries. Okay, capillaries are basically only skin cells. They only consist of an endothelium type cell. Okay, there's a network of capillaries in all tissue in order to ensure that blood is able to get in and transfer nutrients, oxygen, and be able to pick up the waste to move throughout the system. Okay, and thoroughfare channels help to carry the blood from the arteries to the venules. Okay, what capillaries basically are for thoroughfare channels? It's where they move from the arteries to the veins. Okay, but you move not artery to vein, but you get these little small things called arterioles. You have the venules. So you go arterioles to capillaries to venules, and then from the venules you go to the veins. Okay, these capillaries have what's called a precapillary sphincter that helps regulate the blood flow into the capillaries. If these are open, blood's going to flow. If these sphincters are closed, then it's going to limit the amount of blood that can flow in that direction. So basically it doesn't accept blood coming in very well. Okay, so here we see the capillary bed, or enlarged capillary. Okay, and we can see in comparison the size of a red blood cell is just barely large enough to fit through this capillary. So it's not very large at all. Only small, tiny things can fit in, like a red blood cell. But you can't have 100 stacked on top of each other to fit through a blood clot. So if you have a lot of clotting, you're not going to have very much traffic going through your capillaries, or not much blood flow. Okay. So here we look at an area of exchange where we have a capillary network or a capillary bed in the middle. And up top we see our arteriole, which has a little bit higher pressure. The blood is pumping to the tissues there, and it goes through the capillary network, through the thoroughfare channels and your precapillary sphincters. And then it passes on to the venule, and from the venules it goes to the vein, and it goes back to the heart to get pumped all the way back through the system again. Okay, veins. Veins are basically your go-to guy on getting things back to the heart so you can pump it again. Okay, venules connect to the capillaries and are quite like capillaries, except they're larger in diameter. There is some exchange that happens here, but not near as much as what happens in the capillary, because it's much easier for a blood cell that's going to fit into an opening this large to get out to the tissues than it would for something that's in the venule to be able to get out, because it doesn't just easily pass through. Plus, the capillaries basically have pores in between to where these blood cells can actually move through those and out into the tissues. Okay. Looking at the veins. Okay. Here in the veins, we see that there are 3 tunics. Okay, the tunica vincia, tunica media, and the tunica intima. Sounds very familiar, right? Sounds kind of like an artery. Well, there's a couple differences. Okay, they're kind of more like, if you were going to look at the musculature artery as far as what's going on as far as the way it's made up. But the diameter is larger and there's less pressure. So there's not as much need for a whole lot of elasticity. But they're fairly elastic. Okay, arteriosclerosis. When you get older, your arteries might tend to clog. Okay, your arteries don't have the elasticity as what they used to have. They can't allow the blood to flow at a high rate. So you get your large arteries, your aorta, and your coronary arteries. Well, over time, they start to not expand so much, and they start to collect cells, and they start to get hard, and then you get to atherosclerosis. This is where the deposition or the depositing of material builds up, like high cholesterol, builds up in the arteries and prevents blood flow because of the development of plaques in those arteries. Okay, so here we can see in this vein we have three layers here. We're looking at the endothelium. We have the vessel wall. I'm looking at an artery here. Our atherosclerosis here. And we can see the atherosclerotic plaque building up. And notice the size of the chamber has gone from extremely wide here in comparison. And it keeps necking down as you get closer to where the atherosclerotic plaque has built up. So it can prevent the blood flow because there's no channel left for it to flow through, basically. Okay, pulmonary circulation. Okay, the pulmonary circulation helps to move blood to and from the lungs. The pulmonary trunk arises from the right ventricle and divides to form pulmonary arteries. Okay, which, remember, those are the only arteries in the body that carry blood that does not have a high oxygen content. And then these arteries, these pulmonary arteries, project to the lungs. This is where gas exchange is going to happen again. Once again, capillaries this time, instead of giving oxygen to tissues, oxygen is going to be absorbed in the lungs and carbon dioxide is going to be exchanged or given off as a waste product here. From the lung, the four pulmonary veins then return blood to the left atrium. Okay. Here we look at the systemic arteries. Okay. Arteries carry blood from the left ventricle of the heart to all different parts of the body. Okay, make sure you study all the different arteries and veins, remember, especially the ones in the trunk and head. I know there's a few test questions about those, and we'll have more about that coming up. Okay, the aorta. Okay, the aorta leaves the left ventricle. Okay, remember the left ventricle is the one that pumps the blood to the body. It is the most powerful chamber of the heart. So you have to have the most awesome, the most flexible, the one that can handle the most pressure artery of the body in order to pick up that blood when it leaves the left ventricle, and that would be the aorta. The aorta has different parts to it. It has the ascending aorta going up, okay, aortic arch, and then the descending aorta that goes down towards the bottom, moving the fluids towards your lower extremity. Okay, and it consists of the thoracic arch and the abdominal aorta. So the thoracic aorta provides blood flow to areas of the chest, and the abdominal aorta provides blood flow to your visceral organs. Coronary arteries branch from the aorta itself and supply the heart as well. So here we're looking at those of the chest cavity. Remember, there will be a test question over these arteries, so make sure you know what they are. Okay, know what the common carotid arteries are, the left and the right. If you know the left, you know the right, just make sure you know the name. Okay, the subclavians. Okay, make sure you know what the brachiocephalic is, the aorta, the thoracic aorta. Come on, look at the aorta. Right here. Thoracic means it's going through the thoracic cavity. The abdominal aorta is where the descending aorta goes into the abdominal area. Okay? Then you have the muscle that separates the thoracic cavity from the abdominal cavity, the diaphragm. Make sure you know all of these different parts. Okay. arteries to the head and the neck. Okay, these arteries branch from the aortic arch and supply the head and the upper limbs. Okay, so you have your brachiocephalic that divides to form the right common carotid and the right subclavian. The left common carotid, the left subclavian are vertebral arteries that branch from the subclavian arteries. Okay. The common carotid arteries and the vertebral arteries will supply the head. Okay? The common carotid arteries divide to form the external carotids and the internal carotids. External supply the face and the mouth. The internal carotid supplies the brain. Very important, right? To most of us anyway. Alright, vertebral arteries join with the cranial cavity to form the basilar artery, or the basilar artery, which supplies the brain. Okay? And the internal carotids and the basilar arteries contribute to cerebral arterial circle. Okay, so here we're looking at the veins, the arteries of the head and the neck. Okay, so look at some of our major ones, especially our temporal artery. Find your temple. Temporal artery is going to flow right by that location. It also flies down to the zygomatic bones and your cheeks. Okay, you also see those here in your face, your facial artery, your lingual arteries. Okay, superior thyroid artery that goes right to your thyroid gland. Okay, your subclavians down here, brachiocephalics. Okay, superior temporal artery, we already talked about. Okay, we'll start from there and branch back down. Posterior auricular artery, that goes to your ear. Auricle goes to your ear. Okay, occipital artery, occipital part of the head, it goes directly to that area. Maxillary, okay, maxilla. Okay, your bones up here, you know, and then you got your mandible. Okay, is there a artery for the mandible? Is there a mandibular artery? No. What supplies blood flow to the mandible? Okay, that would be the facial artery, and the lingual artery goes and supplies blood to the what? Oh, the tongue, right? Sublingual, under the tongue. Lingual refers to the tongue, so lingual artery supplies blood flow to the tongue. Okay. Alright. Okay, so here, pay close attention to this chart. The major arteries of the head and thorax, because remember, there will be at least one test question about the arteries of the head and the thorax. Maybe like 4, maybe like 5, who knows. If you get the luck of the draw, you might get 7, but who knows. There will be at least 2, minimum. Could be as many as 7. Okay. Alright, so here we look at the brain itself, and we're talking about the arteries here. We got the internal carotid artery coming out right here. Then we have the cerebral arterial circle. Why is there a cerebral arterial circle? Come on. That's question number 1. Why is there a cerebral arterial circle? Why is it there? It's not because of the spinal cord. The spinal cord's down here. Okay. While I'm on my soapbox there, answer question 1-1 and upload it to the PowerPoint section. Okay, so here we're looking at the different brain arteries here. The basilar artery, vertebral artery. Okay, go over those. These won't be tested quite so hard, but you might end up with a few of these questions. So be prepared about the arteries of the brain. Okay, arteries of the upper limb. I know you're going to get a few questions on this. The subclavian artery continues without branching. Okay, subclavian goes outwards to the limbs. Okay, and it becomes the axillary artery, and then eventually the brachial artery. Remember, the brachial artery is where you take your blood pressure. Okay, divides into and then the brachial artery divides into the radial and ulnar arteries to provide blood flow to your lower arm. The radial artery supplies the deep palmar arch, and the ulnar artery supplies the superficial palmar arch. Okay, both arches give rise to the digital arteries supplying blood flow to the hand and the fingers. Okay, so here we can look at the arteries of the upper limb. So we see the axillary artery. Okay, it branches and becomes the brachial artery. Very important to know those two: axillary, brachial, radial, ulnar. Okay, subclavian. You better know subclavian in every possible angle that you can. Okay, all right. So now these main arteries here. This chart's going to help you out. Shows how the subclavian artery is connected to the chest and the back, and the subclavian artery branches out and forms the axillary artery. Axillary artery becomes the brachial artery and supplies blood to the arm. Okay, brachial artery branches, becomes radial artery, ulnar artery, what it supplies blood to, and so on and so forth. Review that chart, know the information. Okay, branches of the aorta here in the chest and abdominal cavity, or as we might call it, the trunk of the body. Okay, so know the arteries of the trunk. Okay, so we start up top with our normal ones that we've been looking at a lot: your carotid arteries, your subclavians, and then we have the aorta. Let's see where the aorta goes. We got the thoracic aorta, and then we go down into the abdominal aorta. Okay, supplies blood to the liver, stomach, spleen, intestines, everything. Okay, it's got to have blood in order to keep going on. So make sure you know some of these. Okay, abdominal aorta is good. You need to know that. You need to know what the celiac artery supplies blood to. Okay, you need to know about the superior mesenteric artery. What is that? What is mesenteric? Okay, superior and the inferior mesenteric artery. Okay, what is mesenteric? Why does it need blood? Come on. Simple questions coming from that. Thoracic aorta and the branches. Okay, in the thoracic cavity, we got some really well-defined branches going on. You got the visceral branches that supply thoracic organs, and you got the parietal branches that supply the thoracic wall, or the muscles of the chest. Okay, the right common carotid, right subclavian, left carotid. Okay, now let's look at the aorta. From the aorta, we see that those are branching off, going up towards the head and the neck region and the upper limbs. Okay, what else is coming off the aorta? The ascending aorta, we see those that we mentioned before. Okay, you got the aortic arch, and then coming down, you end up with the posterior and the intercostal arteries, thoracic aorta, and your visceral arteries branching off of that, and then you have your superior phrenic. Okay, what is the phrenic? Okay, when that word comes out, it's phrenic artery. Okay, question number 2 for you: what organ does the superior phrenic artery supply blood to? Then you have the diaphragm. Okay, abdominal aorta and its branches. The abdominal aorta has visceral branches that supply blood to abdominal organs, and then you have parietal branches that supply blood to the abdominal wall. Okay, so we can go over those here, looking at the iliac arteries down towards the towards the bottom of the diagram, as well as the lumbar arteries. Lumbar supplies to the muscles of the back and the abdominal wall. Okay, phrenic. What is phrenic? And when we heard this before, inferior, we saw superior phrenic arteries before. Now we got inferior phrenic arteries. Okay, then we have the suprarenals, renal arteries, and the suprarenals. Suprarenals are going to supply blood to the what? There was some gland that you learned earlier, right? Oh, yeah. It supplies some major neurotransmitters to the heart. The what? Alright, they're found on top of the kidneys. Oh, yeah, they're the adrenal glands, right? Adrenal glands are important to the heart. They must have really good blood supply going to them, right? Alright, so then you have the kidneys there getting supplied by the renal arteries. And then you have your gonadal arteries that supply blood to the gonads of the male and female reproductive system. Okay. Abdominal aorta and its branches. The visceral branches are paired and unpaired. Oh, wait. They're paired and they're unpaired. Okay, what we really mean is that some are paired and some aren't. Okay. The unpaired arteries supply the stomach, spleen, and liver, the celiac trunk. Then you have the small intestine and the upper part of this large intestine, which are supplied by the superior mesenteric. And then you have the lower part of the large intestine, or the colon, which is supplied by the inferior mesenteric. Okay, then the paired arteries that supply the kidneys, adrenal glands, and the gonads. Okay. Look at the paired. Okay, so you got the iliacs. You got your renal arteries, you got your left and your right there, and you got your suprarenal arteries, your left and your right. Okay, branches of the aorta. We've already gone over these. Make sure you know these fairly well. Okay, very important, especially for this chapter. There's a lot of anatomy here. Okay, very good chart here. It goes over all the different parts of it. You can look over this on your own. Study it extremely well. Yeah, your test is going to reflect the importance of knowing where these arteries are and how they branch. Okay, arteries of the pelvis. The common iliac arteries. The iliac crest, on top of the pelvis. Okay, the iliac arteries would be those that are found in the area of the pelvis. They arise from the abdominal aorta and the internal iliac arteries, and they branch from the iliac arteries. Okay, and the visceral branches supply the pelvic organs, and the parietal branches supply the external genitalia. The arteries of the lower limb. The external iliac arteries branch from the common iliacs, and the external iliac continues as the femoral artery and then as the popliteal artery. Popliteal artery divides to form the anterior and posterior tibial arteries. Okay, tibial arteries are going to supply your tibia and your fibular bones and those areas around them, as well as the plantar areas. The plantar areas are those of the foot, which form the distal arteries are going to arise there. So here we see the femoral artery. Okay, very large artery. A lot of blood flow here. It's got to supply enough blood flow to most of the parts of your lower limbs. Okay? Because most of your arteries are going to branch off that femoral. Okay? Either up top or down the bottom. Are going to start off from the femoral artery. Okay. Make sure you know the femoral artery. Oh, did I say, yeah, you need to know the femoral artery. What about the femoral artery? Yes, that one right there. Yeah, that femoral artery, or that femoral artery, Know them all. Okay, popliteal artery is pretty good. Okay, you need to know that it goes behind the knee. Okay, it supplies blood flow down there to the lower limb. Okay, tibial artery, posterior and anterior versions. Fibular artery, distal arteries, those are going in the toes. And then we've got the common iliac, external iliac, and the inferior vena cava. Hey, wait, we're talking about arteries. We have the inferior vena cava showing up here. Well, we'll get to the veins in just a moment. Okay, major arteries of the lower limb. Okay, make sure you're able to understand the most important ones. iliac, the femoral, the popliteal. Okay, very important. Tibial, you should be able to figure out if you know the name of the bone. Okay. Fibular is going to branch off the posterior tibial. Okay, and then you have those digital arteries down there in your toes. And in the foot, you have the dorsalis pedis artery, and then the lateral and medial plantar arteries, plantar and then pedis, dorsalis pedis. Okay, systemic circulation. Well, so far we've talked about the blood going one direction. Now we got to talk about it going back, the recycling system. Okay, we have the veins. The three major veins returning blood to the heart are the superior vena cava, that returns blood from the head, neck, thorax, and the upper limb. And then you have your inferior vena cava, the one that snuck in a couple of slides back, that supplies blood back to the heart from the abdomen, pelvis, and the lower limbs. Okay. And you also have the coronary sinus. Okay. Coronary sinuses. The heart. Okay. Veins are of three different types: superficial veins, deep veins, and sinuses. So let's look at the major veins. Okay, this is a very large overview. We're not going to go over all of them, but I want you to pay close attention to the superior vena cava and how they branch from the superior vena cava, and the inferior vena cava, and your branching patterns coming off the inferior vena cava. Okay, the veins of the head and the neck. The internal jugular veins drain the dural venous sinuses and the veins of the anterior head, face, and neck. The external jugular veins and the vertebral veins drain the posterior head and neck. So let's check these out. Okay, so we look at the internal jugular vein, how it drains the head going down. We got the facial veins, the face. Okay, the ophthalmic veins, cavernous veins, inferior sagittal sinuses. Okay, superior sagittal sinus. And then you have your transverse sinuses. There's lots and lots of different sinuses in the head. It's full of them. Okay. Okay, you get your temporal vein. You remember your temporal artery. Okay, the retromandibular vein, which the superficial temporal vein branches from. Moving on down. Okay, before it even branches into that, it was the external jugular vein. Okay. You have your facial veins, lingual veins, and superior thyroid veins that are branching off the internal jugular vein. Remember, you have the external and the internal jugular veins. Okay, and below this you have your subclavian vein. Oh, remember, you have the subclavian artery going around the shoulder, subclavian around the shoulder, artery, and the vein around the shoulder, subclavian. Okay, let's look down the closer in the heart. Okay, we got the return. It's coming back into the right atrium, okay, and the inferior, superior vena cavas have blood that enters the right atrium, okay, and we see the left brachiocephalic veins and the right brachiocephalic. Brachiocephalic is where the veins branch off from the superior vena cava, okay, and we see a couple of important veins on the left there. Not quite so as much as the others that we've discussed so far. Okay, remember to follow along on these charts. These charts are going to be very helpful in helping you understand the way the blood flows from one vein to the next and how they all branch from one major vein, just like the arteries did. Okay. Veins of the upper limb. Deep veins are the small ulnar and radial veins of the forearm, which join the brachial veins of the arm. The brachial veins drain into the axillary vein. The superficial veins are the basilic, cephalic, and the median cubital. Okay, the basal veins become the axillary vein, which then becomes the subclavian vein, and then the cephalic vein drains into the axillary vein. I mean, it's a complicated system, but it's not too complicated because really it's all one system that is given different names depending on where it branches and what it gives blood to, or what it takes blood from, both ways. Okay, the median cubital connects the basilic and the cephalic veins at the elbow. Okay, so here we see the blood vessels in the arm. We saw the arteries before. Now we're going to look at veins. Okay, so we see the subclavian up top. Remember, it goes through the shoulder. It's going subclavian. It's going underneath the clavicle. That's why it's subclavian. It goes under the clavicle. Okay, comes into the arm, and then you have the cephalic vein, and then you have your axillary veins, brachial veins. Okay, you have lots of veining in the lower arm and in the hand. Digital veins, the palmar arches, all of those in the hand. Okay, make sure you know subclavian, the axillary vein, the brachial veins. Okay, more so than the others, but definitely know those and be able to understand where the other ones are and what they are. Digital veins, superficial and deep palmar arteries, radial veins, ulnar veins, radial, radius, ulna. Okay. Veins of the thorax, the left and right brachiocephalic veins and the azygos veins return blood to the superior vena cava. Okay. The azygos and the hemiazygos and the left and right brachiocephalic vein return blood to the superior vena cava. Okay, the veins of the abdomen and the pelvis. Ascending lumbar veins from the abdomen will join the azygos and the hemiazygos veins. Okay, veins from the kidneys, adrenal glands, and gonads will then directly enter the inferior vena cava. Okay, the veins from the stomach, intestine, spleen, and the pancreas connect to the hepatic portal vein. Okay, going towards the liver. The hepatic portal vein then transports blood to the liver for processing, and the hepatic veins from the liver join the inferior vena cava. So check those out. Here we see the hepatic veins, and we see the inferior vena cava there, and the right renal vein, all in this area right in here. Okay, the right gonadal vein, the aorta, how those cross, and they're right next to each other, covering the same area. Right, common iliac vein. Okay, know where your iliac is going. Iliac crest going into the pelvis. Okay, remember all of these organs and where they're located in relation to the arteries and the veins. Okay, hepatic veins, hepatic portal system, moving blood to the liver for the liver to filter that blood and clean it up. Okay, your gallbladder, liver. Okay, what are they being drained by? Okay, hepatic veins. Okay, the gallbladder is being drained by the cystic vein. What drains the stomach? The gastric veins. Oh, that one's pretty easy to remember, right? Spleen, the splenic veins. Okay. What about the small intestine? What's feeding that, or what's taking the blood from that? Superior mesenteric vein. And then your lower or your descending colon. Okay. It's being drained by the inferior mesenteric vein. Okay. Review figure 18.24 to figure out or help you with the details on how the blood vessels interact with each other and how they branch. Branching patterns are very important when it comes to arteries and veins. Veins of the lower limb. The deep veins are the fibular or the peroneal, the anterior tibial and the posterior tibial veins. The popliteal vein, very, very, very important to know the popliteal vein, femoral, and the external iliac vein. Okay. Superior veins or superficial veins are the small and great saphenous veins. So here we see the common iliac vein coming in, as well as the external iliac vein. Then we go down into the deep femoral vein, the femoral vein right in the large middle right here. Okay, the one that's making the most impact here is your great saphenous vein. The great saphenous vein is going to start branching heavily in the foot. Who saw that coming, right? Okay, the popliteal vein. Popliteal vein is going to be found right there in the knee, the popliteal cavity. Okay. Now the branching pattern is here in figure 18.28. Just like I said before, knowing the branching pattern will help you determine what artery or what vein that we're talking about is. Okay, blood pressure. What blood pressure basically is a measure of the force exerted by blood against the vessel walls. And the blood moves through the vessels because of blood pressure. And it can be measured listening for Korotkoff sounds produced by turbulent flow in arteries as pressure is released from a blood pressure cuff. Okay. So those of you unfamiliar with checking blood pressure should pay extra attention to this slide. For those of you that understand this fairly well, we're going to move on after talking about systolic and diastolic pressure. We'll throw back to chapter 17 talking about systolic and diastolic pressure. The greatest pressure in the arteries occurs when the ventricles are contracting. That is systolic pressure. The time in which the ventricles are relaxing and the aorta, or I'm brainless right now. Okay, atrium, are contracting and the ventricles are relaxing. It's called the diastolic pressure. That is where the pressure is the lowest in the arteries. That would be diastolic pressure. Okay, so here we see the sphygmomanometer. Sphygmomanometer. Okay, and we're going to measure arterial blood pressure here using the stethoscope. So we notice that the heart is beating over a period of time. If you were able to listen to this, which I'm sure most of you have heard before, okay, you would hear a very, very distinct heartbeat at times in which you either have systolic or diastolic pressure. Okay, and you would read the cuff accordingly. So if you do not hear the sound until you reach 1/120 on the cuff, that means your sound would predict your diastolic. And then you stop listening. Oh, what? That's your blood pressure. Keep hearing it. Still hearing it at this point. Where do you stop here? Okay, let's figure out where we're going to stop here. Okay, you still hear it now. You're at the lowest part. Oh, when you fall below that wave, you no longer hear it. So 80 would be your bottom number, 120 would be your top number. Systolic, 120, 80, diastolic. If the wavelengths aren't the same or the pressure isn't the same, you cannot hear the sound. Alright, so looking at systolic and diastolic pressure, and then we have the mean blood pressure. So the mean blood pressure is going to be the pressure in the veins, in the arteries are going to be between the diastolic and the systolic pressure. So basically your diastolic is your maximum pressure at that time period, and systolic is your maximum, alright, I hope I said that systolic is your maximum pressure at that given period of time, and diastolic is your minimum pressure at that given period of time. And notice that it is very distinct in your aorta. the arteries, and then by the time you get to the arterioles, capillaries, and the veins, venules, and vena cava, there's not much difference between the blood pressure from the systolic to the diastolic. But there is a very, 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 very distinct difference in pressure in diastolic and systolic when you're in the arteries, especially the aorta. Okay, physiology of circulation. Blood flowing through a blood vessel? Yeah, the amount of blood that moves through a blood vessel in a given period of time. Okay, it will be directly proportional to pressure differences and is inversely proportional to resistance. Resistance is the sum of all the factors that inhibit blood flow. Okay, resistance increases when blood vessels become smaller or viscosity increases. Viscosity is a resistance of a liquid to flow. So something that has a high viscosity would be honey. You can't pour honey out easily, but you can pour water out easily. Honey has a high viscosity, water has a low viscosity. Okay, most of the viscosity of blood results from the amount of blood cells in that blood. It slows down the flow because there are actually cells in the blood. Okay, the viscosity of blood increases when the hematocrit levels of the plasma decreases. So we're pouring blood in. Arterioles change. Resistance changes. Notice that some of them have resistance, some of them don't. Those with no resistance fill up their tubes more quickly. So basically we got our pump here simulating the heart, and we got our reservoir, our arteries, and then it's pumping through outflow tubes, your arterioles. Alright, physiology of the circulation. Alright, blood flow through the body. Mean arterial pressure will be very equivalent to the cardiac output times peripheral resistance. Oh, wait, was that a mathematical formula? Mean arterial pressure is equal to the cardiac output times the peripheral resistance. So the vasomotor tone is a state of partial contractions of blood pressure. Okay, and the vasoconstriction increases the vasomotor tone and the peripheral resistance, whereas vasodilation decreases vasomotor tone and peripheral resistance. Blood pressures tend to average between 100 millimeters of mercury in the aorta and drops all the way down to 0 millimeters of mercury in the right atrium. The greatest drop occurs, however, in the arterioles and the capillaries. Alright, let's start the flow. So here we see the venous return. It's pumping out. We got dilation compression going on there, dilation compensation going on there. Alright, now the arterioles have changed. Notice that some of them are constricted. Let's start our blood flow. Okay. We got a lot coming out in the first one. The arterioles of the second, third, fourth, and fifth aren't quite so great. Alright, our arteries have a lower amount of blood. Now let's see what happens when we start our flow. Okay, same thing's going on. Decrease in pressure. Okay. Alright, let's look at the comparison there. We can see the venous return has changed. The pressure was the highest on the left. Okay, but we had restriction of all the arterioles. Okay, only the first arteriole was changed from the second to the third, but what did change? The pressure changed greatly. Okay, and from the second to the third, we see that with the higher pressure, most of it comes out in the first opening possible. Okay, by the time it reaches the next set, it's fairly consistent. Excuse me. Alright, physiology of the circulation. Pulse pressure and vascular compliance. Pulse pressure is the difference between the systolic and the diastolic pressure. So it's the pressure in between. Pulse pressure increases when the stroke volume increases or the vascular compliance then decreases. Vascular compliance is a measure of the change in the volume of blood vessels produced by a change in pressure, and the pulse pressure waves travel through the vascular system faster than the blood flows. The pulse pressure can be used to take that pulse. Okay, there's certain areas or pressure points where you can take the pulse of a person. Okay, most common places in radial artery, found right there in the wrist. Okay, the common carotid artery. Okay, is also common, or the temporal. But also notice that you can take it in the facial artery, axillary, the brachial, the femoral artery, posterior tibial, dorsalis pedis, and then the popliteal artery found behind the knee. Physiology of circulation, blood pressure, and the effect of gravity. In a standing position, hydrostatic pressure caused by gravity will have this effect. It increases the blood pressure below the heart, and it decreases the blood pressure above the heart. Capillary exchange and regulation of interstitial fluid volume. Okay, capillary exchange occurs through or between endothelial cells, so blood cells actually pass between skin cells, basically. Okay, diffusion, which includes osmosis, filtration, are primary means of capillary exchange. Filtration moves materials out of the capillaries, and osmosis moves them into the capillaries. And then there's a net movement of fluid that occurs from the blood into the tissues, and the fluid gained by these tissues is removed by the lymphatic system. Okay. So here we can see the diagram of the exchange of fluid across the walls of capillaries. Review these steps and be very prepared to answer questions about them. Okay, remember, depending on the changes in osmolarity, blood's either going to flow in, blood's going to flow out, cells are going to come in, cells are going to go out, fluid's going to go in, fluid's going to go out. So we have lots of things going on.
At the arterial end of the capillary, the net filtration pressure is equal to the net hydrostatic pressure minus the net osmotic pressure. The net filtration pressure is 13 millimeters of mercury. This causes fluid to move from the capillary into the interstitial fluid. At the venous end of the capillary, the net filtration pressure is equal to the net hydrostatic pressure minus the net osmotic pressure. The net filtration pressure is minus 7 millimeters of mercury. This causes fluid to move from the interstitial fluid into the capillary. Approximately 9/10 of the fluid that leaves the capillary at its arterial end re-enters the capillary at the venous end. About 1/10 of the fluid passes into the lymphatic capillaries and returns to the bloodstream via the lymphatic system.
Okay. So control of blood flow. Blood flows through the tissues is controlled and matched closely to the metabolic need of the tissues. Okay, there's local control of these things. The response of vascular smooth muscle to changes in tissue gases, nutrients, and waste products. And it also changes if the metabolic tissue or metabolic activity of the tissue and it increases, and then the diameter and the number of capillaries in the tissue will then increase over time. Nervous system and hormonal control. The sympathetic nervous system, the vasomotor center in the medulla, the medulla, controls the blood vessel diameter. Other brain areas can excite or inhibit the vasomotor center. Epinephrine and norepinephrine can cause the vasoconstriction in most tissues, and epinephrine causes the vasodilation in the skeletal and the cardiac muscles. Muscular arteries and arterioles then control the delivery of the blood to the tissues, and finally the veins are the reservoir for the blood. Venous return to the heart increases because of the vasoconstriction of the brain, not the brain, the veins, and it increases blood volume and the skeletal muscle pump with valves. Okay, so here we see the medulla here in the brain being our vasomotor center. Okay, we see the sympathetic pathway where it moves from our sympathetic chain through sympathetic nerve fibers to either the arteries or the veins. Regulation of mean arterial pressure, MAP, mean arterial pressure, is proportional to cardiac output times peripheral resistance. Okay, short-term regulation of blood pressure. The baroreceptors are sensory receptors sensitive to stretch. They're located in the carotid sinuses and the aortic arch. The baroreceptor reflex changes peripheral resistance, heart rate, and stroke volume in response to changes in blood pressure. Okay, baroreceptor reflex control of blood pressure. Make sure that you have reviewed these steps and are very well versed in this process. Okay, know that the baroreceptors in the carotid and aortic monitor blood pressure, and the action potentials are conducted through the gasopharyngeal and the vagus nerves to the cardioregulatory and vasomotor systems. Okay, increased parasympathetic stimulation of the heart will then decrease the heart rate, and increased sympathetic stimulation will increase the heart rate. So parasympathetic decrease, sympathetic will increase. Okay, increased sympathetic stimulation of blood vessels increases vasoconstriction.
Increased blood pressure stretches the carotid arteries and aorta, causing the baroreceptors to increase their basal rate of action potential generation. Action potentials are conducted by the glossopharyngeal and vagus nerves to the cardioregulatory and vasomotor centers in the medulla oblongata. As a result of increased stimulation from the baroreceptors, the cardioregulatory center increases parasympathetic stimulation to the heart, which decreases the heart rate. Also, as a result of the increased stimulation from the baroreceptors, the cardiovascular center decreases sympathetic stimulation to the heart, which decreases heart rate and stroke volume. The vasomotor center decreases sympathetic stimulation to blood vessels, causing vasodilation. The vasodilation, along with the decreased heart rate and decreased stroke volume, bring the elevated blood pressure back toward normal. If the initial problem were a decrease in blood pressure, the activities and effects of the baroreceptors, cardiovascular center, and vasomotor center would be the opposite of what is illustrated.
Okay. So the short-term regulation of blood pressure, epinephrine and norepinephrine are released from the adrenal medulla, and as a result of the sympathetic stimulation, they increase the heart rate, stroke volume, and vasoconstriction. Peripheral chemoreceptor reflexes respond to decreased oxygen, leading to increased vasoconstriction. Central chemoreceptors respond to high carbon dioxide or low pH levels in the medulla, leading to increased vasoconstriction, heart rate, and force of contraction. Seeing this ischemic response. central nervous system, ischemic response. Okay, the adrenal medullary mechanism. Okay, so you see the medulla oblongata is stimulated due to increased stimulation or physical activity, and it sends information through the sympathetic chain, through sympathetic nerve fibers to the adrenal, and the adrenal gland kicks out epinephrine and norepinephrine, and that's going to speed up the circulatory system. The chemoreceptor reflex control of blood pressure. Okay, chemoreceptors in the carotid and aortic monitor oxygen, carbon dioxide, and the pH of the blood. Okay, chemoreceptors in the medulla oblongata monitor blood carbon dioxide and the pH. Decreased oxygen and increased CO2 and decreased pH decrease parasympathetic stimulation of the heart, which increases the heart rate. Decreased oxygen, increased carbon dioxide, and decreased pH increased sympathetic stimulation of the heart, which increases the heart rate and force of contraction. Decreased blood oxygen, increased carbon dioxide, and decreased pH, increased sympathetic stimulation of the blood vessels, which increases vasoconstriction. So when the heart rate is increased, typically vasoconstriction is also occurring.
Chemoreceptors in the carotid and aortic bodies monitor blood oxygen, carbon dioxide, and pH. Impulses from these chemoreceptors are conducted to the control centers for heart and blood vessels via the glossopharyngeal and vagus nerves. Chemoreceptors in the medulla oblongata monitor blood carbon dioxide and pH. Decreased blood oxygen, increased carbon dioxide, or decreased pH decrease parasympathetic stimulation of the heart, which increases the heart rate. Decreased blood oxygen, increased carbon dioxide, and decreased pH increase sympathetic stimulation of the heart, which increases heart rate and stroke volume. Increased sympathetic stimulation of blood vessels increases vasoconstriction.
All right. All right, so long-term regulation of blood pressure. Okay. Through the renin, angiotensin, and aldosterone mechanism. Renin is released by the kidneys in response to low blood pressure. It promotes the production of angiotensin 2, and then it causes vasoconstriction and an increase in aldosterone secretion. Aldosterone helps maintain the blood volume by decreasing the urine production. And then vasopressin ADH mechanism, okay, antidiuretic hormone, causes ADH release from the posterior pituitary in response to a substantial decrease in blood pressure. ADH then causes vasoconstriction and helps maintain blood volume by decreasing urine production. Okay. So here we see the renin, angiotensin, aldosterone mechanism. Be fairly familiar with it. Okay. How this happens, make sure that you know the major players here, like your aldosterone, your vasoconstriction's going on, your angiotensin, okay, and that your kidneys are going to be triggered here in the process producing renin. Also pay attention to the fact that vasopressin mechanism here is going on. It's releasing ADH, antidiuretic hormone, causing constriction. Okay, long-term regulation of blood pressure. The atrial natriuretic mechanism causes the atrial natriuretic hormone released from the cardiac muscle cells when atrial blood pressure increases, so it then stimulates an increase in urinary production, causing a decrease in blood volume and blood pressure. The fluid shift mechanism causes fluid shift, which is a movement of fluid from the interstitial spaces into capillaries in response to a decrease in blood pressure to help maintain blood volume. Okay, it's illustrated right here. Make sure you pay attention to when homeostasis is disturbed and when homeostasis would be restored in this process. Okay. Exercise. What happens in exercise? Exercise causes local control of a mechanism, increases the blood flow through exercising muscles, which lowers the peripheral resistance. So increases blood flow by reducing peripheral resistance. Okay. Cardiac output then increases because of increased venous return, stroke volume, and heart rate. Vasoconstriction in the skin, kidneys, and the gastrointestinal tract, and the skeletal muscle tract, both non-exercising and exercising, increase peripheral resistance, which helps prevent a drop in blood pressure. Okay, blood pressure then increases despite an overall decrease in peripheral resistance because of increased cardiac output. Circulatory shock occurs due to baroreceptor reflexes, and the adrenal medullary response increases the blood pressure as well. The renin-angiotensin-aldosterone mechanism and vasopressin mechanism increase vasoconstriction and the blood volume. The fluid shift mechanism increases the blood volume as well. In severe shock, the chemoreceptor reflexes increase vasoconstriction, heart rate, and the force of contraction. In severe shock, despite negative feedback mechanism, a positive feedback cycle of decreasing blood pressure can then eventually cause death. Okay, here's a nice review that's found on page 562. Please review and become ready for our exam. I will have that posted online, which opens on this Thursday, but you have all the way until the 19th of October, I believe, to complete that. Okay. Make sure you get caught up on your lectures, get caught up on your homework, and I will see you guys soon. Not sure when. Hopefully I won't be working too many 16-hour days anytime soon. Have a great weekend,